This section is going to be focused on design codes. We're going to look at the general design procedure, we'll look at different limit state designs, and then we'll see how those were applied in the development of the design codes that we use in reinforced concrete design. Our learning objectives for this section are to differentiate between design and analysis, explain the basic performance objectives and design code philosophies, list and explain the different types of limit states, specifically looking at allowable stress design, ultimate strength design, or LRFD, plastic design, capacity design, displacement-based design, and performance-based design. Then we'll see how we can apply plastic design to calculate the plastic capacity of a structure. And then we'll look at how to design a member using capacity design procedures. And then finally, we'll explain, you'll be able to explain LRFD and summarize the types of variability in reinforced concrete design. The first thing that we want to do is be able to distinguish between analysis and design. In analysis, we're given a structure and loading, and we want to determine the strength, stiffness, internal forces, and/or the reactions from that given structure and loading. So in our reinforced concrete design, typically we'll be given the cross-section of our beam or our column and the location of our reinforcement. In design, we have a given span and loading, typically, and our design is the process of creating a structure that meets certain performance objectives in the face of numerous considerations. So for us, we'll be designing several different members. This would be the basic given parameters for the design of a reinforced concrete beam with our given loading and our given span and a given concrete strength and grade of reinforcing steel. Although we can typically in design choose our reinforcing strength and our concrete strength. In design, we're typically given our client's needs and priorities. From these, we'll choose our structural parameters, our dimensions and reinforcements, and concrete strength and other things. After we choose our structural parameters or our cross-section shape and reinforcement, then we need to analyze our structure. Then with our analysis, we can check it against our design demands to make sure that we meet all of our performance objectives with an adequate level of safety. If we don't, then we need to go back and redesign our structure. If we do, then we have our final design. Here are some of the considerations, constraints, processes, and players that are involved in the design process. When we're designing, we need to consider our functionality. So what's the purpose or function of the structure that we're designing? The economy, what's our budget? Safety, what are the loads that are going to be on the building or bridge? And how can we safely design it? Durability, we want to make sure that our building or bridge is going to last its intended service life. Then we'll have certain constraints, so project funding, physical limitations, our client knowledge. Our clients are not structural engineers, so this can be a constraint. And then also our engineering fees. Engineers don't make that much for designing a structure compared to the overall structure cost. So we need to design structures efficiently in terms of our use of time. Then our process, we consider our client's needs. We'll develop a concept and then come to our system and member design. And there are several different players that are involved in the design process. So the client, the person funding the construction of the building or bridge, the community in which the building or bridge will be located, the government bodies, or municipalities, state or federal, that are over and have jurisdiction over the city or township or wherever the building is or bridge is located. All the architects and other engineers that are involved in the design. A structural engineer just works as part of a team that will design and construct the building. And then us, the structural engineer, and then the contractor who actually builds it. So whatever we design needs to be constructible by the contractor. There are four main structural engineering objectives that we must achieve when designing a structure. The first is appropriateness. So our structure needs to fit its intended use and it needs to be aesthetically pleasing. If it doesn't fit its intended use, then it's not functional, and if it's not aesthetically pleasing, then people won't enjoy coming to it. The second is economy. The overall cost of the building or bridge needs to be within the client's budget. If it's too much, then the client won't be able to afford finishing it, or they'll need to take out additional loans. If it's too little, then we left some money on the table, and we could have added some functionality to the building or bridge. Structural adequacy. So a structure needs to be able to carry loads safely and not experience excessive cracking or deflection. So this will be the primary focus of our course, is designing our members in our building or bridge to carry the loads so that they won't experience excessive cracking or deflection, so serviceability, and they'll also be able to carry ultimate loads safely, so strength considerations. And then finally, maintainability. A structure needs to be able to last as long as it's designed for its service life. So we need to make sure that our structure is durable. Here are some examples where engineers failed in one of the structural engineering objectives. The first is the Pruitt-Ego housing development, which was constructed in 1956 and based on a formalism worldview. In formalism, everything in nature is mathematically verifiable and nothing else really matters. So you have flat roofs, smooth facades, and cubist shapes. The Pruitt-Ego housing development became infamous for crime by the mid-60s. And they ended up demolishing it in 1972 to cheers from the neighborhood. So this shows that people are more than just machines, and engineers need to a certain extent, also consider aesthetics. The second example shown on the right is the Sydney Opera House. The Sydney Opera House was based on an expressionism worldview where nature can learn a thing or two from my imagination and emotions. So in this worldview, you have a lot of, in this type of design, you have a lot of organic or biomorphic shapes. So the problem with this is that nature doesn't always agree with your imagination. So the Sydney Opera House ended up taking 14 years to construct, and it ended up costing 20 times the initial estimate. So this is a failure in economy. The Tacoma Narrows Bridge near Tacoma, Washington is an example of failed structural adequacy. The Tacoma Narrows Bridge opened to traffic in July 1st of 1940, and it was the third largest suspension bridge at the time, behind only the Golden Gate Bridge and the George Washington Bridge. The Tacoma Narrows Bridge had a very slender deck, and the wind caused excessive deformations or excitations of the deck, so much so that the bridge was nicknamed Galloping Gertie. The bridge eventually collapsed under 40-mile-per-hour winds on November 7th, 1940, only 4 months after being open to traffic. So this is an example of a failed structural adequacy. An example of failed maintainability or poor durability is the Ringling Bridge in Sarasota. The Ringling Bridge is a post-tension segmental bridge that was built in 2003. And only 8 years after its construction, the bridge already has or had excessive corrosion requiring substantial maintenance. So this bridge is still being rehabbed because of the issues with the post-tensioning tendons. And this is an example of failed maintainability or poor durability. That brings us to our discussion of design codes. And first we'll look at the main goals of design codes. There are 4 main goals. The first is to protect public safety. Buildings that are designed by the code shouldn't fall down. So having the design code helps to protect the public. Design codes also protect the engineer. Engineers can follow these codes to ensure they are doing safe designs. So they don't need to reinvent the wheel every time they're doing a design, but they can follow a design code. Design codes also protect the owner. Owners can know that their building is properly designed when an engineer follows a design code. And finally, design codes can help guide engineers. So engineers can follow a code to know how to design members. This last goal to guide engineers wasn't always wasn't always a goal of design codes. It's only kind of recently become a goal, and this has led to very large codes. So ACI and AASHTO have become very large documents because they're now helping guide engineers. But all codes use some type of limit state design. This is the process that we'll need to follow when conducting a limit state design. And this process is taken into account in many of the building codes or specifications. So first, we need to identify all possible failure modes or limit states, primarily safety and serviceability. After identifying these possible failure modes or limit states, we need to determine and assign an acceptable level of safety against exceeding each of these limit states. And then finally, we can design our structure to achieve this level of safety for each of the limit states. And failure of our structure is when any of the limit states are exceeded. One type of limit state is the ultimate limit state. Some examples of ultimate limit states are the collapse of part or all of the structure, a loss of equilibrium as a rigid body or overturning, such as the building shown on the right that was caught in a landslide. We have rupture of our tendon or reinforcement that can lead to collapse. There are several examples of failed pre-stressing tendons leading to collapse of structures. We'll have instability or buckling of our structure, which can happen in our longitudinal reinforcement, and this can lead to collapse. And then finally, we can also have a collapse due to deterioration. And this is an example of a pedestrian bridge that collapsed due to corrosion of the pre-stressing strands. Next, we have damage limit states or service limit states. These can include premature or excessive cracking, such as ASR or DEF cracking that can occur in concrete elements with reactive aggregates or where the heat of hydration was allowed to get too high initially. We can have excessive deformations causing damage to non-structural elements. So this is an example where the John Hancock Tower in Boston, excessive deformations allowed the windows to fall out. So you can see that here. We can have permanent inelastic deformations. This can be a damage limit state. And then finally, environmental conditions like corrosion or abrasion. And this is an example of extreme corrosion in the bottom of a box beam that's left the pre-stressing strands exposed. So the next limit state that we're going to talk about is a service limit state. And service limit states mainly have to do with human perception. So these can include service deformations under vertical or lateral loads, which can affect machine alignment or human sensitivity or drainage. So we can perceive large movements at the top of skyscrapers under wind loading, is one example. Also, we have service vibrations. So this can affect or be caused by machine operation, and also human sensitivity. So when crowds are jumping on stadium bleachers, there can be a vibration that's caused that can make people feel uneasy if it's too large. And then we also have unsightly cracking. So cracking may not be a reason for concern for the engineer, but it can make the user feel uneasy about the safety of a structure. So we need to be conscious of how our structure behaves under service loading so that our users feel safe and comfortable in the structures. We next need to discuss risk and what are acceptable levels of risk. So here's a table showing the risk of death for various activities. The left column in this table signifies avoidable risks. So these are risks that a user or somebody needs to participate in to be at risk. So somebody needs to race motorcycles to be at risk of dying because of motorcycle racing. So some other examples are mountain climbing, mining, swimming, commercial air travel. So these are risks that people can avoid. The right column are unavoidable risks, and these are risks that are risks to the entire general population. So it's activities that people cannot avoid doing. So everyone needs to drive, everyone needs to be in buildings or walk outside, and the general public also gets vaccines. So these are risks that can't be involved. And you can see that the risk of death for these activities is lower than that of some of the other avoidable risks. The people who developed the design codes and all of the factors that go into the design codes needed to consider several questions on risk. The first is what's an acceptable level of risk? Under this question, they needed to think about how important's a person's life, how much is a person's life worth, and ultimately, how much is society willing to pay to save lives? We can design buildings to be as safe as we want them to be, but the safer we design a building, the more expensive it'll be. So there needs to be a balance there. The second thing that they considered was what are the generally accepted maximum acceptable levels of risk? So going in and out of a building is unavoidable. So what are our levels of risk that are generally accepted for unavoidable risks? And then finally from this, we can come and figure out a probability of failure for a structure and look at the probability of failure over the design life of the structure. And then we can use this probability to figure out all of our load and resistance factors. This can be represented in a cost versus probability curve. So here, the red line would be how we would design a structure or the behavior of a structure. So we have some kind of load probability and then some kind of cost to repair the structure. So a high probability event should have a small amount of damage to it. So a high probability event should only cause minor cracking or no cracking. As we decrease the probability of the event, we can have more damage that occurs to the structure. So we may reach the elastic limit for a lower probability event, and then come up and have wider cracking or yielding, then maybe crushing or spalling, and then finally evacuation and ultimate collapse. And these events will cost more to repair, but they're less likely to happen. So we need to think about where on this curve we want our minor cracking to occur, our elastic limit, and some of these other points. There are different ways to achieve our desired level of safety, and these are all under the category of limit state designs. We have ultimate limit state designs, which we'll go through, which include allowable stress design, ultimate strength design, which is also known as load and resistance factor design, plastic design, capacity design, displacement-based and performance-based designs. And then we have some service limit states that we can also consider, where we have empirical methods for design and performance-based design methods. The first limit state we're going to look at is allowable stress design. In allowable stress design, we apply service loads to the structure. So we have no load factors. Then we evaluate the forces and stress using linear materials. So we're working in the linear range of our stress-strain relationships. And what we want to do is we'll design our structure so that we have a max material stress that's observed from our loads using our linear elastic materials. And we design it so that it's less than our allowable material stresses. In ultimate strength design, we apply ultimate factored loads to the structure. So we factor our dead load and we factor our live load. Then we evaluate our section demands using our material properties. So typically we'll use our yield strength in our steel, and we'll use the compressive strength of our concrete. And our design objective is to have our factored forces less than or equal to our factored capacities. So in ultimate strength design, we're reducing our capacity and we're factoring and increasing our forces. The plastic limit state design is similar to the ultimate strength design, but it looks at the structure as a whole and looks at what is the capacity of the structure as a whole. In the ultimate limit state design, you're looking at the strength at a section. In plastic design, you're looking at what is the strength of my member or structure as a whole. So how can loads and moments be redistributed after we have failure at a section? The procedure for plastic design is we first will apply loads to a structure until we form a hinge. So in this fixed beam with a distributed load, we'll have maximum moments at the ends of the member. So this is where our hinges will form. Then after the hinges form, we'll draw a new structure and apply additional load until a second hinge forms. So our fixed beam with hinges at the end is just a simply supported member. And this simply supported member can take additional load. So we apply the additional load until we form another hinge, which will happen at the middle. So after our second hinge forms, now we apply the hinge, and we can see that our structure now is kinematically unstable. So we can't apply any more load. So the total collapse load is then the summation of the load required to cause the second hinge and the load required to cause the first hinge. Now, take a break from the presentation and look at the example problem for the plastic design procedure. We're next going to look at several components of our plasticity theorems. There are three main components. The first is our equilibrium principle. And this is just whether our internal forces equal our external applied forces. And equilibrium is always going to be achieved. The second is our yield criterion. So essentially, do our applied stresses exceed or are they less than our available material strengths? And then finally, our collapse mechanism. Is the mechanism that we have on the structure, does it cause collapse or not? As I said, in our plastic limit state design, our equilibrium is always going to be achieved. So this is always going to be true. A lower bound plasticity theorem is always going to satisfy equilibrium and our yield criterion. So we're always going to have a safe design if we're using a lower bound theorem. This means that our predicted failure load will be less than or equal to our actual failure load. This means that we may not have a collapse mechanism. So we may not have a predicted load equal to the load that'll cause our collapse mechanism. An upper bound plasticity theorem is one where we have equilibrium and we have a collapse mechanism that forms. So in an upper bound theorem, we're going to always have a predicted failure load that's equal to or greater than our actual failure load. So in an upper bound theorem, we may have an unconservative design. Our uniqueness plasticity theorem is when both our upper and lower bound theorems are satisfied. So this means that equilibrium is achieved, we have a collapse mechanism, but we also have a safe design. So we fall right here in the middle of our Venn diagram. So this means that when our uniqueness plasticity theorem is satisfied, we have a predicted failure load equal to our actual failure load. The capacity limit state design is a design method that aims to control explicit failure mechanisms and sequences. So essentially, we design for a certain failure type, and we prevent the failure or prevent the structure or member from failing in every other failure type. So the procedure is we first select how we want the member to fail. So this typically means we want our member to fail in flexure versus shear, or we want a certain component of the member to fail rather than another. So we want a hinge to form in the beam rather than the column. Then we would provide sufficient strength for that mode of failure using LRFD. We'll detail that mode of failure for a ductile behavior. We'll then determine the probable strength for that mode, considering the actual material strengths that we may have versus what we specified. Then we'll determine the forces required to reach the probable strength. And then we'll design the other elements for those forces that are caused to reach the probable strength. And take a break now and go to the capacity design example problem. For some members, force becomes a poor measure of performance and damage in the inelastic range. So for these members, we may want to design our structure to take or sustain some type of inelastic deformation rather than a force. So this can be done using a displacement-based design. So in our displacement-based design, we design our structure to take some kind of displacement rather than a force. So this is mainly done for seismic design. Another type of design is performance-based design. In performance-based design, we design a structure to reliably achieve a target performance objective. So we typically look at the forces that can be applied and the likelihood of that force or event that can happen to the structure, and then the damage that's caused as a result of it. So frequent events, we still want to be in the elastic zone. Occasional events, we can start going inelastic, but we still want to be operational. Rare events, we still want our building to stand up, but we can take a little more damage. So we want people to be able to evacuate or take shelter in the building, but it may not be salvageable after the event. So in performance-based design, we're considering the system performance and not just the component performance. Here's another way of looking at our performance objectives. We can say we want a fully operational building under frequent events, and maybe we want an operational building under occasional events, and a life-safe building under rare events, and a near collapse building under very rare events. So this would be a basic performance level objective. We can then decide if our structure is more critical, like maybe it's a hospital or a power plant or something, or holds some type of nuclear material or something like that. We could have an essential objective or a safety critical objective. So in a safety critical objective, we would want to be fully operational under even rare events and operational under very rare events. So we can design a structure to meet safety critical objectives, but it will be much more expensive. So the benefit of the performance-based design is it allows owners to make informed structural decisions with a cost-benefit ratio explicitly evaluated. So an owner can consider how the cost of replacement and casualty rate and downtime in days will line up with his performance objective. So we'll line up with the base shear force, the likelihood of that event happening, and then the repair cost, the casualty rate, and the downtime. So the owner can make a more informed decision and decide how much money he or she wants to put up front to design and build the structure. The next topic we're going to focus on is understanding the LRFD design procedure and how it was developed. The basic requirement for LRFD is that our factored design strength is greater than or equal to our factored required strength. So our strength reduction factors are less than 1, and these account for variability in our material strengths, construction tolerances, and failure mechanisms. And our load amplification factors are typically greater than or equal to 1, and these are affected by our variability in our loading. Before moving on, I want to do a quick review of probability and 2 ways that we can represent our data sets. The first is with our probability distribution. The probability distribution is essentially at any one of these points, we have the number of observations within a certain range divided by the total number of observations that were done over this, or that are contained within this data set. The cumulative probability distribution, on the other hand, accumulates the total observations from the left to whatever point we're looking at, divided by the total number of observations. So at some point here, this would be the summation of all the observations to the left divided by the total number of observations. So with a cumulative probability distribution, you start at 0 and you end up at 1. With a probability distribution, we have some kind of bell-shaped curve that normally will develop. Most data sets will fit a normal Gaussian distribution, shown here. So in this distribution, we can figure out the total amount of observations that are contained within any number of standard deviations away from the mean. So if we're 1 standard deviation away from the mean, we have about 68% of our observations contained. If we move out 2 standard deviations away, we have about 95% of our total observations. And if we move out a 3rd standard deviation, then we're about at 99.8% of our observations will be contained within 3 standard deviations. Our load and our strength will typically follow a normal distribution. So if we plot our load observations and our strength observations for any one set desired load and desired strength, we can then factor our load and reduce our strength. And the goal of LRFD is to limit the number of occurrences where our reduced strength on the lower end of this Gaussian curve is less than our factored load on the right side of this Gaussian curve. So we want to limit this area here, or the point where our reduced strength is greater than our factored load. To properly limit the probability that our factored load will be greater than our reduced strength, we need to look at 6 main different steps. So the first, we're going to define our loads. Then we're going to define our load variability. Then we'll look at and define our member strength variability. We'll select our format for factor implementation. So we'll focus on ACI in this section. And then we'll select a target reliability, and then finally determine our load and resistance factors. So the first thing that we need to do is define our loads. The first type of load that we'll define is our dead loads. So these dead loads include any slabs, beams, or columns, or any other permanent members or loads that are constant in magnitude. And these typically make up the structural system within our building or bridge. The next type of load is live load. So these can be loads from people or occupants, loads from trucks, or loads from our traffic in our design line live design lane load. And we have other types of loads then that we need to consider. So we can consider our snow loads if we're in colder climates, our wind loads, so either from tornadoes or hurricanes, and then also seismic loads if we're in seismic active areas. Next, we can look at our load variability. So different types of load have different variability. Our dead loads are going to have different variability from our live loads. So dead loads are less variable than live loads. So this means that we can have smaller load factors for dead loads than our live loads. We also know that our maximum loads have differing probabilities of occurring simultaneously. So if we have a larger area, there's less variability in our live load than in a smaller area. And this is accounted for by having some live load reduction factors based on area in some codes. We now move from our load variability to our member strength variability. So here we'll look at different variability that we have in the material, in material sizes, and also in member sizes. So the first here is a variability in our steel strength. So we may specify 60 KSI yield, but that doesn't necessarily mean that we'll get a 60 KSI yield strength material. In actuality, we'll likely get a yield strength much higher than 60 KSI, depending on what type of steel we use. Also, our yield strength is going to be dependent on the size of the bar. So a smaller bar will typically have a higher yield strength than a larger bar. And this is because larger size bars are more likely to have imperfections. We'll also have some variability in our concrete material strength. So although we may specify a 3 KSI concrete, this doesn't necessarily mean that we'll have a 3 KSI concrete. We'll likely get a concrete strength around 4 KSI or higher. Also note that the variability in the concrete strength will decrease with higher concretes, as shown here. We'll also have some variability due to in situ effects in our concrete. So sometimes it's difficult to achieve adequate consolidation, so we'll have some variability because of placement and compaction. We may have temperature effects due to size, so we'll have some variability in thickness. There's curing will impact the strength, so we may have some variability based on the exact curing conditions. And then our time effects are really difficult to estimate, so there will be some variability due to the shrinkage, creep, and residual stresses in our concrete. We'll also have some geometric variability that will affect our member strength. The first is with our steel bar area. The specified area of our reinforcement is not necessarily the actual area of our reinforcement. We can have actual areas of our reinforcement that can be plus or minus 2 or even 4% of the actual area, and this will have an impact on our strength of our member. Another type of geometric variability is the member dimension variability. The dimensions that we specify in our design are not the exact dimensions that will get built. There's some difference between the design dimensions and the as-built dimension. This can be plus or minus 0.5 or even 1%. So this will affect our member strength. We typically will specify some kind of tolerance, or there are specified tolerances, which essentially tell us what's the allowable difference between the design and as-built dimensions. Another type of geometric variability is the location that the rebar is placed. can be variable in this section. So you may specify the reinforcement be located at one location, but it may sag up or sag down depending on how it's tied to the rest of the cage and how the cage is secured. So there can be some variability that's accounted for in the code in the actual location of the reinforcement versus what you designed. The resistance factors, however, do not account for misplacement of reinforcement. This is an example from some bleachers that were built for a racetrack in Austin. The design location of the reinforcement was at the top of the section in this cantilever bleacher. The contractor placed the reinforcement at the bottom of the section because it was easier for him to build. And the section had some cracking that occurred at the top, so they had to go back and retrofit with some post-tensioning in the top. So this type of mistake is not covered by our strength reduction factors. We will also have some analytical variability. So within our analysis, the estimated strength, even if you knew the exact properties for your material strengths and the exact areas and locations of your steel and the section dimensions, there would still be some variability when you go to estimate the capacity compared to what the measured capacity would be. So we need to account for this analytical variability as well. Now that we've looked at all the different types of variability that we can have, we need to select a format for our factor implementation. The two main types are allowable stress design and load and resistance factor design, LRFD. With allowable stress, we have a reduction factor that we apply to our material strength, and all of our variability for our loads and our strength are accounted for within this reduction factor. In the load and resistance factor design, we reduce our strength with our reduction factor, and we magnify or amplify our load with this amplification factor. So these are two different ways that we can account for all of the variabilities that we talked about. ACI and AASHTO both use the load and resistance factor design for concrete design. So that's what we're going to focus on in this class. The next thing that we want to do is select our target reliability, or our consequences for failure. And to do this, we'll create a new plot with our safety margin. Our safety margin Y is just our strength minus our loads. So if we have a positive Y, we have a safe design. If we have a negative Y, this means that our loads are greater than our strength and we have failure. So our probability of failure we can then find as this area highlighted in red. We can also define a safety index, and the safety index is a beta, is the number of standard deviations between the 0 point, or y equal to 0, and the mean for all of our y values, or the mean of our safety margins. Our safety index, or beta, is going to give us some insight on the probability of failure. A beta of 0 means that we have a 0.5 probability of failure. As our beta increases, our probability of failure decreases. We can then come and assign a beta factor to different load combinations, and we can also assign a beta factor to different member variabilities. And we can do this to develop our load and resistance factors, which we'll do next. Here are the different load combinations that are found in the ACI 318 code. We have load combinations including dead load and live load and snow and wind loads, and also seismic loadings. And you can see that the different load combinations have a different primary load. In this course, we're going to focus on the dead load, where the dead load's primary or the live load's primary. These are some of the resistance factors that we're going to use in this course. So we have some resistance factors for typical flexural failures. Resistance factor of 0.9 if we're a tension-controlled flexural member, or 0.65 or 0.75 if we're compression-controlled. Tension-controlled being a ductile failure and compression-controlled being a brittle failure. So you can see how the resistance factor changes, and you need to reduce your strength less for a ductile failure mode. And here are some other typical resistance factors for shear, bearing on concrete, and the shred-and-tie method. These are all more brittle failure mechanisms, so you can see that these are lower or smaller reduction factors than the tension-controlled. So we have a higher reduction when we have brittle failure mechanisms. This is a list of references for further study on this topic.